you again for your report. And the last topic and presentation in our subsection is the development of set of test system prototype for an FPGA-based model. And the report authors Roman Dячок, Alina Klim, and Andriy Lukashik. Будь ласка, sorry, please.
Hello to everyone. I will share my screen and
Everything is okay, please.
so hello to everyone. My name is Roman Dячок. I am from Lviv Polytechnic National University from department Specialized Computer System Department. Oh, sorry. Sorry. I need to reshare screen. Okay. So we want to present you a development of a test system prototype for an FPGA-based model. So what main aims do we have? This work aims to develop and implement an HLS-based design verification framework that use a TDD approach to address the current challenges of verifying system implemented with FPGA technology. The main objective includes evaluating the effectiveness of HLS and in accelerating FPGA-based development and facilitating program verification, developing of a testable environment for modeling hardware components, and comparing the obtained results with a reference model, implementing TDD principles to ensure the correctness of designs that combine FPGA with other process technologies. So, why did we do that research? The main goal of our research was to develop a prototype test system for FPGA-based system at different levels of abstraction, and we decided to start from high level synthesis HLS. So, what is HLS? High synthesis HLS is gaining popularity for speeding up FPGA development and simplifying program verification. It broadens the FPGA market by enabling both software and hardware developers to evaluate different architectures. However, HLS struggles with remotely assessing project credibility. Verification tests comparing results against a golden model that are crucial but time consuming. Recent studies indicate that ensuring design correctness, especially when combining FPGA with other technologies, can take up to 70-80% of the total project effort. This makes verification a major challenge in FPGA based projects, adding extra requirements for validating HLS generated models. So, from what our system consists of, so we decided that our prototype test systems must consist of seedling as a test framework. We should use TDD as a test method for test creation, and also we use Altera FPGA Day 0. So a few words about principle of verification test. So we choose 5 in our opinion key properties. So first, it's speed. Testing procedure is fast enough to be considered a compiling issue for developers. Also, a verification test must be isolated to avoid any dependencies on other assessments. It must be repeatably. Test must be repeatable. Also, it must be self-test. The test should give a logical consist with is it pass or fail, and it should be adequate to avoid errors. Unit tests should be performed before writing working code. The result of the hardware check is separate report which describes in detail the feature of the execution time. And in our opinion, Seedling pass all these key facts. Now I will tell you a few words about Seedling workflow. So Seedling allows both temporal and functional introspection of a hardware components by incorporating TDD into the hardware development process. You can significantly increase productivity, improve quality, and achieve high test coverage as has been demonstrated in the software industry. The figure illustrates a typical user flow of seedling, highlighting the manual automatic steps and the primary inputs and outputs of each process. The framework is used for its Cyclone 5 Altera FPGA diagonal architecture, resulting in scripts and components designed according to the Cyclone 5 technology, the Quartus 2 tool chain. So it will be in my opinion, it will be helpful to say a few words about seedlings work from user point of view. So seedling as a unit test framework have very friendly API interface with all necessary APIs for testing integer value, float values, or something else. Also, it have automatically generated mocks, but unfortunately, stubs must be write by a developer. So now I will tell you about seedling verification frame. So the validation frame consists of various components. So first, it's pre-designed, it's ready-made components. Second, it's customized, tailor-based on the design stage. Also automatically created, it's generated by system. So testing, a few words about testing infrastructure components. It's unit test. This use seedling extension macros to test individual code units. Also test runner that must execute each block of test sequentially. Another component is simulation and virtual twins in FPGA. The FPGA bitstream includes a component to be tested and auto-generated mocks, a test manager for a seedling library. Also, another component is digital representation. So, digital representation consists of functional digital representation, is digital design unit test dude model, RTL representation, register transfer level model of the dude, physical bitstream on FPGA, the actual bitstream loaded on FPGA. Also, it communicate with dude. The test program must communicate directly with dude, except for functional testing derived from C. And the last but not the least, its task manager is connected to the bus and received messages containing rules and data to control the testing process of execute design unit test. So now I will tell a few words about overview the test manager and youth communication framework. So in this slide it's in its general view, and in the next slide I will show you particular in our case. So overview in general of test manager and youth communication framework. It includes AMBA technology. The test manager, youth, and communication partners are connected using AMBA technology, facilitating data transfer. Next is data transfer. The test manager connects to the bus, receiving commands and data from dude execution. Data transfer occurs throughout external DDR memory, storing data and execution test. So role of a transfer as test manager. It acts as a DMA with additional capabilities like measuring task execution time. It reads from DDR, executes due task, and saves outputs back to DDR for compression. So another, it's automatic mock generation. Here is mistake. Here I write stop, but it should be mock generation. RTL logic and internal data are generated automatically, ensuring seamless communication between FPGA virtual duplicates and the test manager. Another, its virtual twin implementation maintains the same signature as RTL logic layer, allowing the test runner to operate without changes, maps due to input-output channels to memory. Another benchmark suite includes algorithm for various domain to benchmark HLS tools. Framework design is modular and adaptable to different platform on an FPGA. So in previous slide, as I already told, we speak about a general overview. Now we will speak about particular our case. What we use for seedling testing infrastructure for HLS project. So we use framework components. It's unit test, test runner, and co-simulation virtual twins. Also, we use test runner. As I already mentioned, it's automatically create using a Ruby script from a Unity framework. It initiates the test process and remain unchanged regardless of the abstraction level Also, it's designed under test, include functional digital models, virtual twin, computer-generated code executed during implementation, and also test managers. This hardware component provide a standardized protocol and interface for virtual duplicate FPGAs and dudes. It interrupts transaction and manage communication with dude. So, a few words about results. On this slide, you can see comparison of simulation and execution time. This table compares the simulation and execution time for 12 cores in the CH Stone benchmark suite. And I will tell you a few. Here is a summary of the key points. So first key point, it's simulation time. It's obtained using the co-simulation function in the Quartus 2 high-level synthesis. Next, second key points, it's actual runtime. It's measuring using the built-in seedling validation system. So, what key metrics we compared for understanding is our research good? Its average time, the average time spent in a both simulation and execution, minimum and maximum difference, the difference between hardware execution and simulation time, also latency, the delay which within each core. And what observation do we see? First observation is error margins. Some CH Stone cores show significantly error margin up to 66%. The error tends to increase with the number of test cases. Second is impact of joint simulation. Joint simulation can sometimes lead to incorrect design decision due to difference is how seedling measure onboard delays. So next observation is job queue in Quartus 2 HLS. So Quartus 2 HLS create a job queue with one of the entire per input to the dude design under test. The average time to process test case is measured from when the case are queued, not when they are processed, leading to incorrect time calculation. So in conclusion, uh, what we want to say about validation methodology using seedling. So seedling is a comprehensive system that test hardware components using high-level synthesis. This methodology is beneficial for developing embedded system for an FPGA platform. So
Okay. Okay. Thank you for your presentation. And let me really briefly to ask the question. When you told about the HDL tools from Xilinx, what's the exact tool from the HLS tool chain you mean? Is it Vivado tool from Xilinx, or SDAxle from Xilinx, or newest Vitis tool from
uh,
Xilinx?
thank you for your question, Vivado tool.
Thank you. It's clear, and thank you for your really interesting presentation.